Thanks again, everyone, for joining us here today. Again, my name is Chris Munns. This is Networking Best Practices for your serverless application. A little bit more about me. I currently manage and lead developer advocacy for serverless at AWS. I've been at AWS now for a little over 8 years across two different spans of time working here, and I held a couple of different positions. From a background perspective, though, I come from more of what you might consider a DevOps or an SRE type of background managing infrastructure. However, for the last 3.5 years, I've represented the serverless space and now lead a team of people that create a lot of the content that you might see or read or join us on Twitch or see tech talks like this. And I'm based in the New York City area. So what are we talking about here today? As the title of this talk might allude to, we're going to be talking about the implications of networking on serverless applications. Specifically with a focus around Amazon VPC. Now, when we're talking about a serverless application, I want to be very specific. We're actually talking about an application that is based around AWS Lambda. Now, the word serverless today in the industry means a lot of things to a lot of people, but again, here we're going to be focusing on this concept of Lambda kind of being the core of that. Now, for those of you that are new to Lambda, the way that it works is there's basically 2, maybe 3 components that every serverless application needs. The first is some sort of an event source. So something that is responding to either, say, a request to an API endpoint, to an event that's happening inside of your infrastructure or your application architecture. Could be doing data processing. Today, there are over 100 different services that can invoke Lambda plus its API, which we'll be talking about. You then have a Lambda function. A Lambda function is a bit of code that you've written that runs on the Lambda service in response to an event. Today we have 6 primary languages that we support. We also support the ability for you to bring pretty much almost any language that you could think of via runtime API. And then what that function does is up to you. Talking to databases, data stores, things that are in your network, things that are outside of your network. These are all options that you have that are available to you based on what it is that your application needs to do. And we'll talk a little bit more about that here as well today. So this is an example of a serverless web application architecture. We see here what would be essentially a serverless web app that has its front end hosted in the AWS Amplify console. So Amplify console is a service for hosting static pages. It's for hosting single page applications, essentially also just anything that's HTML, CSS, or JavaScript. Pretty flexible service, a lot of capabilities, not something we're going to be going in depth in today. I can then also be using Cognito to authenticate the users for my application. So Cognito is a managed user store. I can do all sorts of things with storing information about my customers or the users of my application, giving them capabilities like multi-factor authentication, login UIs, stuff like that. And then maybe more pertinent to our conversation here today is the bottom line, which is our serverless app backend, where in this case, I have an API that is powered by Amazon API Gateway that is then invoking an Amazon Lambda function, or AWS Lambda function, I should say. And then that AWS Lambda function then is talking to data in DynamoDB table. So really straightforward, basic application architecture. Now I'm going to change this just a little bit here and make this a semi-serverless web application architecture. And what we see here is everything else remains the same. So Amplify console, Cognito, API Gateway, Lambda, all services that would require no management of infrastructure, no running of servers, no infrastructure management insofar as needing to think about the storage and configuration of the underlying hardware or anything like that. But then we see that my Lambda function in this case is talking to a Amazon relational database service database and an Amazon Elasticache cluster or node. And that could be running either Redis or Memcached. So minor difference here. Now, both of these services that you see here in the VPC, Amazon RDS and Amazon Elasticache, also do not require you to install software or manage virtual machines or containers or anything like that. They do require you to have a VPC, Virtual Private Cloud, which we'll be talking about here today. They do have some knobs and levers around their configuration for memory and storage, and special parameters that apply to those. So slight tweak between the two. And so the question I have is, which one is better? Now, if you're a purist like me, you would say the first, right? That seems pretty obvious. You've got here absolutely no servers to manage, all this scaling capability built in, pay for what you use architecture, high availability, resiliency, redundancy across it. And then if we look at this second one, you know what? This one might be something where you say, well, you know what I have here? I have relational databases, which I know. I have cache services like Memcached or Redis, which I know and I've used before. And so while this may involve some more operational duties for you, given that the majority of what you would do compared to if you're running this yourself is managed for you, you know, it's not that different. So really what I would say is whatever one solves your business needs best is the one to pick. Now that's easy to say, but clearly there's differences here. Clearly there's differences in the configuration, primarily around this little green box here that we have that represents a VPC. There's actually a whole lot of complexity that could be baked into that. And so today we're going to focus on how we can kind of distill and pull that apart. So, you know, how are these two architectures different? How does it impact application design? What sort of work do you end up shifting back on yourself if you take on these challenges or take on these requirements? And that's what we're going to try to help you understand today across covering a bunch of different concepts. So what are we going to cover today? First, I want to help people who are really new to VPC. Let's say that you're a application developer that's not deep in networking. Let's say you're a traditional network person that's not that deep in VPC. Want to help kind of just demystify what VPC is, what the core components of a VPC are, and how to think about that. Next, we'll talk a little bit about how Lambda and VPC work together. So if you do end up needing to have your Lambda functions attached to a VPC, what does that mean? How does that work? What does it look like, you know, kind of behind the scenes? And then lastly, we'll talk about some best practices, gotchas, things to think about for VPC in your Lambda-based applications, so that at the end of today's session, you've got just a ton of direction to take and a ton of, again, kind of best or better practices that you should think about following. So thanks again for joining us here, and we're going to dive into this. Real quick, I want to mention we do have live Q&A happening right now, so you should see here a little Q&A pod. Please feel free to ask us questions. You've got a team of people here that are going to help try to answer as much as we can today. So please keep those questions coming as the presentation's going, and we will try to answer them for you. Cool, so let's get into kind of the basics of Virtual Private Cloud, or VPC. Starting with VPC 101. So what is a VPC? You know, at the end of the day, the way that I like to describe VPC is it allows you to basically carve out your own 4 virtual walls inside of the AWS cloud for your infrastructure. For those of you that are more familiar with traditional physical networking infrastructure, you know, maybe you've configured routers and switches, maybe you've configured entire data centers worth of networking gear. VPC is the closest thing to providing you a lot of the same controls that you would have seen. Basically allows you to create this, again, as in the title, private network inside of the public cloud. That allows you to do a whole lot of things. You can restrict access between resources. You can grant access inside and outside of that VPC. You could really take a VPC and model it to look very similar to how you would do in a physical infrastructure that you were managing, again, with more traditional networking gear. You can also use VPC to connect to other networks. So whether it be via a VPN or a direct connect connection, you could connect to your organization's you know, on-premises or otherwise managed networks, and allow resources in the AWS cloud to talk to those resources in those physical data centers and vice versa. So VPC is really kind of a core foundational product or product suite, if you will, here at AWS today. So why would you use a VPC? Again, we've already kind of stated some of the reasons, but one big one is because you want to use traditional compute-based offerings. This means you want to use Amazon Elastic Compute Cloud, Amazon Relational Database Service, Amazon Elasticache, Amazon Redshift, a whole bunch of services that behave in a more serverful manner. These are things where you're configuring CPU and memory and storage, or maybe you're running the whole virtual machine yourself. Or maybe you're running a container-based offering such as ECS or Fargate. And in that sense, you need that traditional network. It's something that's a requirement of using those services. You might also want to use VPC if you're really looking for the kind of familiar network controls that you've had in running your own physical network. So in this case, it might just be a familiarity thing for you. You think about your stack from the network up and you build accordingly. Many AWS customers have really strict networking security requirements. So for those of you who might be in regulated industries, who might be in the financial world or healthcare or government, you're going to have no choice but to use a VPC. And this might be to controlled egress, to, again, just provide boundaries around things. And so VPC is going to be something that you're kind of living and breathing every day. If you need to connect to other networks, and you want to do that over a private controlled tunnel, or again, something like a direct connect, then you're going to have to use VPC. And then lastly, you might just have a need to use some of the advanced traffic control capabilities for things like cross-account and cross-region connectivity. And so in that case, VPC might also be something for you. Now we'll talk a little bit more later about specifically to your service application if VPC makes sense. But more or less, I find today that the majority of AWS customers are using a VPC. So even if you're in part of your business where, let's say that you're developing applications and you don't really touch the VPC, you're more of a consumer of it, hopefully today will still help you understand some of that. Those of you who are new, who are building infrastructure, this is still good foundational information that you should know. I wanted to bring forward a bunch of resources here for y'all. And so these are all links directly to docs or other sites where you can find out a ton more about VPC. It's really one of the most, I would say, complex capabilities and offerings that we have here at Amazon Web Services. There's a lot of nuance to it. There's a lot to read. And so each of these 4 sources represents, I think, some of the best collections of content. And so I encourage you to take a screenshot of the slide. We'll also be sharing all of these slides with you here in the coming days after this is recorded. But either way, these 4 sources will help get you just a ton more information than we could ever go into in a single tech talk today. Okay, so let's get into some core kind of foundational concepts around VPC. The first is your VPC. So this is the space that, again, you kind of carve out inside of the AWS cloud. And this starts by you defining what is called a CIDR block, CIDR here, which represents the network space that all of the rest of your resources will live inside of. Now, by default, this is just what's called an IP version 4 CIDR block. We do have options as well for IPv6, which is another thing that many of you are starting to have requirements around. The bottom line here around tenancy does not apply directly to Lambda, but this is something that some of you in more regulated industries might run into. Not something that a majority of AWS customers need, but again, just something that can benefit you if you are in one of those regulated industries. So again, VPC, think of it as the widest kind of 4 walls that represents your own little space in the cloud. You can think of it as your data center inside of our data centers. You can think of it as your, if you've ever been inside of a much larger data center, your cage inside of, a larger building. Again, this is your space for your resources to live and connect inside of. So wait a second, I used a term back there, CIDR, what does that mean? For those of you, again, who are maybe a little bit newer in networking, this is an important term to have an understanding of. So CIDR stands for Classless Internet Domain Routing. And basically what it represents is a way of thinking about how IP addresses are made available, how you think about carving up network spaces into smaller spaces, and how to think about basically sizing your resources. And we'll talk a little bit more about sizing a little bit later here. 2 different, again, QR codes for you here. One links to more information about what CIDR is and what it means. And then the second one links to this IP calculator that I found. There's a lot of IP calculators that you could find out on the internet. This was one that I come back to pretty often. And from the previous slide, we see that I gave my VPC network a IP CIDR of 10.1.0.0/16. And so what it means is that my VPC could support up to 65,534 IP addresses. And again, that's just the example for today. But CIDR calculator, really important for sizing. Again, we'll talk a little bit more about sizing here in a bit. But this is what CIDR is, kind of a foundational networking concept. Again, if you're not someone who has spent a lot of time building or designing networks, this might be new to you. If you're someone who's been building and designing networks your whole life, you probably know much more about this than I do. Okay, so inside of your VPC, the next thing that you would do is typically basically break that VPC up into subnets or subnetworks. And essentially, this is a way that you can, again, as the name sounds here, split up the IP range inside of your VPC. There's a lot of reasons you might want to do this. One is just for compartmentalization of resources. The next is to potentially provide routing or security boundaries, to provide, again, just organizational constructs. And typically everything that you do will exist inside of some sort of subnet. So you are required to have at least one subnet inside of your VPC. Many of you, though, will have many subnets of varying sizes across multiple AZs. We'll talk about multi-AZ here as well in a little bit later today. But again, another kind of core concept in networking. Okay, the next core concept that we'll talk about is VPC gateways. Now, there exists today inside of VPC a number of different gateways that provide a number of different capabilities. And much like the name suggests, a gateway is basically a way for your data, your traffic to get from one place to another. It provides I can't use the word gateway to define a gateway. It provides that kind of handoff space between two places. So some of the most common ones you'll run into. The first is an internet gateway. This allows your VPC to have public IP addresses that are assigned to it that exist in the AWS Cloud's public IP space. This means then that those resources that have those public IPs are available on the internet, whether or not they accept traffic or not. So this would be a requirement of being able to have public resources that face outbound, but also to allow traffic outside, from inside your VPC to getting outside of your VPC. So pretty core foundational component. Pretty much almost everyone with a VPC is going to have an IGW. Times when you may not might be if your VPC is just meant to be connected to another VPC, or if your VPC is connected to a VPN tunnel or maybe a direct connect going back to your own data center, and then you have another gateway potentially that's shipping the traffic that way. The next is a NAT gateway. So a NAT gateway is another common networking term and capability. And this is what will allow traffic that might exist inside of a private IP address space or a private subnet to go out to the public internet. We'll talk a little bit more here about what private and public means in a moment. And then lastly, another capability of VPC is something called transit gateway. This is a bit more of an advanced concept for those of you who are in larger, more sophisticated organizations. And we'll talk a little bit more about this here later as well. This allows you to basically connect multiple VPCs together, almost in a hub and spoke model, so that you can allow traffic between different VPCs. So these are, okay, just a couple of examples of some VPC gateways. And again, you see here highlighted in this kind of diagram, this concept of public and private, and we'll come right back to this here shortly. Okay, another core concept of VPC are route tables. So a route table, as per the VPC docs, is a set of rules called routes that are used to determine where traffic is directed. Essentially the way to think about this is that in order for us to reach our NAT gateway and utilize it, in order for our NAT gateway then to be able to speak to the public internet, we need routes that will direct that. Now, every device on the internet, every mobile phone, your computers that you're viewing this from here today, anything that you have that's connected to a network or an internet has routes that help that device know where to connect. So this is a foundational core aspect of the way the internet works. What we see here are two examples of route tables. One that is configured for what I call here again my public subnet, and then one that is configured for what I call here my private subnet. Now they look pretty similar. Both of them say that for my main IP block for my VPC, this 10.1.0.0/16, so my IP space, it's going to use what's called the local target for routing traffic. And basically what this means is that anything inside of this IP space that is part of this VPC can effectively reach anything else inside of this VPC at basically the lowest level of networking. Now I can still have security groups that block things. I can have network ACLS, which we'll talk about here in a moment, that can also block. But this effectively means that things can communicate. Then what you'll see below on the second line of each of these tables is another route that looks pretty similar, but has slight differences between these. So on the public subnet, we were saying that any compute resource that has an IP address in this public subnet that wants to talk out to 0.0.0/0, which means essentially the world, will need to go through the internet gateway. So we're saying here that these will be hosts that will have some sort of public IP address on them in order to talk to the internet gateway. And then they will use the internet gateway as their default route out to the internet. In the private subnet, we see the same rule, but with a different target, in this case, the NAT gateway. And so what this says is that if anything in this private subnet wants to talk to the internet, it needs to first talk to the NAT gateway. And then the NAT gateway, because it's in the public subnet, but the public subnet route table knows that it has to talk to the internet gateway. So you can see here kind of this flow from the bottom of this diagram up to the top of it, where we have to go through these two hops in order to get out to the public internet. And again, that's route tables. So real quick here on this concept of public and private subnets. Essentially, for those of you with a more traditional networking background, this isn't a concept that applies directly the same. You might have a public IP space that's been given to you by your ISP or your networking provider in your data center. This is a slightly different concept in that based on the route tables, what we're saying is that a given subnet has a default route to an internet gateway. Because of that, it can't use any other route to get to the internet. It's going to expect that whether they be instances or other compute resources that are inside of this subnet have a public IP address assigned to them and can use that public IP address. Now, with VPC subnets, you do have the ability to make this be a default option. In this case, if I were to auto-assign IPv4 addresses to my public subnet, every time that I launched a EC2 instance or one of a number of different services, it will automatically make that a publicly available resource. Now you want to be careful here because again, depending on your security group configuration, you could end up leaving stuff open to the internet that you don't want to. And so this is a checkbox that I personally don't usually leave checked, but again, depending on your situation, you might want to. Now, what makes the other subnet private is that it doesn't have these two things. It, first of all, doesn't have a default route to the internet via an IGW. So even with the default route that we saw before, which was through the NAT gateway, that still doesn't allow us out to the internet without going through that NAT gateway. And if we were to assign a public IP address to one of these subnets, it wouldn't be able to route outbound through it because it wouldn't be able to connect outbound through that internet gateway. So again, basically two rules here that make something public: default route to the IGW, and then the ability for, or then resources having public ENIs attached to them. Another core VPC concept, as well as kind of general compute concept in AWS, is security groups. So security groups, traditionally part of EC2 instances and then similar services like that, are essentially a firewall that is wrapped around that resource that has a number of capabilities. So again, tied to traditional compute resources that are inside of VPC, or if you happen to have an account that still has what's called AWS EC2 Classic, then it would apply to those classic resources. But if you have a AWS account that's new as of the last couple of years, this does not apply to you unless you are an old school AWS customer at this point. So a security group is essentially a stateful firewall that wraps around the resource. What does that mean? Basically means that if you have traffic that goes outbound from it, so you make a request out to, say, a website or an API, the response for that will be allowed back in because the security group is statefully tracking that traffic. So this doesn't mean that you have to, as opposed to a stateless firewall, have certain ports open on the high end for responses from traffic. This means the security groups are going to do that for you. So makes it a lot easier to configure security groups versus if you had some sort of stateless firewall that you had to track. And so you can use security groups to create rules that allow you to basically either allow or deny inbound or outbound traffic to specific IPs or IP ranges, services, or other security groups. And by default, the security group doesn't allow any traffic in. So you are only allowing traffic in and creating allow rules. You are not creating deny rules. So the deny is essentially implicit as part of it. And then we see an example here where I have allowed outbound HTTPS and DNS requests. So maybe my Lambda function that we see here in this diagram is talking to a public API, and I want it to be able to both look up the DNS address for that API and then to communicate it with it over HTTPS. And so we see here the rules that are required for that, both for IPv4 and then that little destination that says : /0. It's actually an IPv6 notation. And so that would allow via IPv6 to me to talk to those resources. Okay, network ACLs, another core component of VPC. So a network ACL or access control list is basically another layer of being able to block traffic or allow traffic in and out of resources inside of your VPC. More of a traditional networking concept. So if you are not familiar, again, with doing this in other networks, this could be something that's very new and different to you. And the way that that network ACLs work as well is that they are basically undefined by default. So you have some default network ACLs that are created as part of every VPC, and then you have the ability to go and decide what traffic should be allowed out beside that. Now, these do supersede security groups. So if you have a security group like I had here in this previous slide, and here it says that I can talk to HTTPS on port 443, I could actually have a network ACL that denies that traffic from going through. And so regardless of anyone else in my business configuring a security group, this network ACL would end up basically being able to block that traffic. ACLs are also not stateful. So whereas I mentioned that security groups would automatically be able to allow back in the response from a request, with the network ACL, you have to leave open those high ports. So you would have to specify those ports, again, depending on your underlying operating system or the service that you're using, that would expect a response back on. Again, a little bit more to get into than we can handle in today's conversation, but you can find out all about this in the network ACL docs, which you see linked here below. Okay, so that wraps up core concepts for VPC. Again, we've covered what a VPC is. We've covered subnetting. We've covered route tables, security groups, network ACLs, gateways, the concepts of public and private. This is really just scratching the surface. There's a lot more than you can read about here. And so again, I've brought up these links that you could find a ton of content in here, videos, blog posts, the documentation, an example of building a VPC, which you see here with the second link, the modular and scalable VPC architecture reference deployment. So I definitely encourage you to check out more about this here. All right, let's bring it back to Lambda. So we've talked about VPC, all these concepts. Let's assume that you are, well, let's talk a little bit about why you might want to use Lambda with VPC. But first, a little bit about just how Lambda works. So again, Lambda is a managed compute offering from AWS. All of the compute resources for Lambda are managed by the service itself. So you don't set up any servers, whether they're physical or virtual. You don't run any container environments. You're not dealing with typically things like having to manage pullers off of queues or any, again, the complexity that happens underneath a service such as Lambda. Now, your Lambda function, when it's executing, though, the code that you write does have a number of things that it can do. So that code would have access to the underlying host network. So you can talk out via the network, you can talk out via ports, you can talk out via the internet or network that it lives inside of. One important thing to note about Lambda is that when you have a Lambda function, we can capture any output that you create and automatically capture that data into CloudWatch logs. Now, we'll talk a little more about this here a little bit later, but essentially that ends up happening through the underlying worker environment, not through the network. This is, again, important to come back to here in a bit. And then one really key thing here, this is such an important aspect about Lambda, is that there's basically just one knob that you turn for performance, and that's the amount of memory that's been configured for your function. As you turn that number up, you get more CPU capability and more network throughput. So as I go from the default of 128 to 256, I effectively double the CPU and network throughput. This is a really, really important thing to note. Whether you have a CPU intensive workload, or maybe you're pulling in really large files from S3, or maybe you have a database query that returns a whole lot of data, you may not expect that the CPU and the network might be your essential tight spot here, but it can. And so tuning the memory is the number one thing that I recommend to customers who talk about performance issues with Lambda functions. Okay. So again, by default here, network or Lambda resources are all managed by the Lambda service team. So these are not compute resources that you see in your account in any kind of traditional sense. All of these resources live inside of a network that is controlled by the Lambda service. So all of the core underlying networking stack, essentially the VPC that it lives in are technically controlled by the service. And there's nothing you can do to turn that off. That is how this works by default. When your function executes, it has full access to the public internet. So there is no way in the default model for Lambda for you to restrict access outbound from Lambda functions or allow just to a specific place. It has full access to the public internet per the networking of the AWS region. And by default, again, there's no way that you can control this with a Lambda function not attached to a VPC, which again, we'll talk about here in a moment. Now, when it comes to actually being able to invoke your Lambda function, this is again something that is only today available over the public internet. So whether you're using a service like Amazon API Gateway, or you are processing data off of SQS, or a Kinesis stream, or a DynamoDB stream, or a IoT device, those things are going to talk to the Lambda Service API. The Lambda Service API is going to actually go and invoke your function. And today that is available only via the public internet. Now, the function environment itself has no direct access inbound to the network. You don't have to worry about someone who's scanning the internet, finding your Lambda function, and finding something inside of your code in like a traditional manner of scanning ports and IP addresses. It's not something that's possible. The only way that Lambda talks through out to the internet is from inside itself outbound. And then because it has that stateful mechanism of the security group to it, then that allows traffic back in. Okay. But again, with this, you can do a lot of things. So by default, you can talk to all of the public AWS API endpoints. You can talk to all of the IP addresses that exist out on the internet. You could talk to your on-prem data centers via, again, public IP space. All of this is stuff that's just available out there. And again, when it comes to talking to other AWS services, the key aspect here is that the function has a policy attached to it that allows that to happen. So just because these APIs exist doesn't necessarily mean that the function would have the permissions required to do that. But again, this all exists out there. So if you say accidentally grant too much capability to your function, and someone were to put nefarious code into your application, that could do anything possible out on the internet, talk to any other endpoint. And so this is definitely a concern that many developers and many organizations have. Okay, so I mentioned how this allows you to connect to public resources, but what about when you want to connect to non-public resources? Again, as this exists right now, Lambda would live outside of your VPC, and it could only talk to the public addresses that are represented from your VPC. And so let's talk a little bit more here about what it means to attach a Lambda function to a VPC that you own. And it's really key here that we know this to be called attaching or connecting a function. One thing you don't want to say is that the function lives or is inside of the VPC. This might sound like splitting hairs. This might sound like some gray space between some terms, but it's really, really key to understand what we're going to talk about here about how the Lambda function connects or again, attaches to the VPC. So this is a distinction that really matters. It is a misconception that I find trips people up very often. And I was talking publicly on Twitter about this talk recently, and had posted a picture of this slide, and I got a ton of people reaching out just saying, I don't understand, what does it mean, what does it matter? Or people saying, oh my God, yes, this is something that has tripped me up before. So again, really important to understand the distinction that the function does not live inside of the VPC, like an EC2 instance would, like an RDS database would, etc. So when you configure your Lambda function to be attached to a VPC that you control, what ends up happening is that we have to create a network connection into that VPC. The way that works today, and it's been this way for just a little over a year now, is that we have a virtual device, which is called a VPC to VPC NAT, or a V2N for short, that gets created and attached into your VPC. And this basically allows us to NAT or bridge between the VPCs that are managed by the Lambda service and then the VPC that you've configured it for. When this happens, it basically, again, treats that Lambda function as an extension of your VPC. All of the traffic, all of the routing, all of the security of your VPC becomes applied to that Lambda function. That Lambda function loses the ability to talk out to the public internet via just a public interface. It is unable to talk to AWS service APIs. It is going to have to go through your VPC then to talk to those other things. We'll talk more about this here. You're also required to configure a security group and then subnets for this V2N to connect into. We'll talk about the importance of that here as well. Again, V2N is a networking capability that we first announced back in September of 2019. This was something then that we rolled out into the VPCs of customers that had Lambda configured for VPC. It replaces an older model where we used to attach individual ENIs to Lambda function environments. That model had a number of downsides to it, which are all actually mentioned in this blog post off of the QR code that you see here. One thing that you might find is that there were a lot of people who used to talk about this old model. And so you might find blog posts out there that are dated from 2 years or 3 years ago, or even just in the summer of 2019 that are completely inaccurate after that point. So it is really important to know that when you are reading about networking in Lambda, that you refer to our documentation, you refer to this blog post, you refer to talks like this, or anything else that came out after September 2019, because it's very, very different from what was here before September 2019. So this V2N virtual device that we created, it behaves, again, very differently from this previous model for connecting into a VPC. The first is that we have changed when this resource gets created. And this was something that used to cause a number of cold start pains, essentially the latency felt when your environment first starts up. So with this, what happens is we now create these V2N virtual devices and the elastic network interfaces for them. Anytime that you create a new Lambda function or update the networking configuration of one. So you basically block that action until it has created this virtual networking device. Because of the underlying technology of V2N, something that's called AWS Hyperplane, we're able to get much greater traffic volume through fewer ENIs or elastic network interfaces. This means that we're able to use many fewer of them. It means that we need to spin up, less of them overall, which improves overall startup time and cold start performance and so forth. And then again, we're not consuming those resources inside of your VPC. Now we can share these across multiple different functions that use the same security group and subnet configuration. So if I have a subnet in my VPC that I call subnet 1, and I have another one called subnet 2, and then I have a security group called Lambda security group, and I configure a function for all three of those things, so subnet 1, subnet 2, and that one security group. And then I create another Lambda function, the exact same. It is going to use the same V2N essentially into my VPC. And so all of the invocations, all of the same configured functions will use that V2N to reach in without having to consume as many resources as the old model. it's a massive, massive difference in terms of the work and complexity involved. It greatly reduces the impact to your Lambda functions. Again, this is a completely managed virtual device. It's highly available. It automatically scales. And maybe the best part here is that it costs you absolutely nothing. So you do not pay for these V2Ns. You do not pay for the scale of them or anything like that beyond normal networking charges that you would pay just as part of using compute resources in AWS. Here's a brief example. This is from the launch post, again, a year ago, showing the before model and then the after model. And what we see here is that the initialization of these two functions changes drastically. We also see that the performance overall is a huge difference insofar as the total time that it takes for these functions to execute. So the total duration that you see here. So previously 14.8 seconds. After this, under 1 second. This is actually a function that does quite a bit of work. So it does take a couple hundred milliseconds to execute. But what's important to understand here is that the actual time spent in spinning up this virtual interface is greatly reduced. And actually, I should say that these diagrams represent a time before we started creating the resource before that first cold start. So actually, you would see almost no impact from your functions being configured to a V2N at this point. Okay, so some things to note about V2N, right? With all of this this complexity and stuff that's happening, there are some trade-offs. There are some things that you need to understand. While we do heavily reuse the elastic network interfaces, and they can handle much more throughput than they used to in the past, there is potential that your workload might still require them to scale up. So as they scale up, they will consume more IP addresses inside of your subnets. Again, this is completely transparent to you, but as we talk here about sizing subnets in a little bit, becomes an important factor. They do also require you to have your Lambda functions have create updates and I believe delete calls on network interfaces. And so this is such that when the Lambda service is actually going and starting or actually creating your function and configuring it for you, it has the ability to call the networking services behind the scenes. V2N interfaces cannot be public. So what does this mean? When you create a virtual, when you attach Lambda to your VPC and it creates the V2N, even if you put it inside of a public subnet, the V2N is not able to have both a public and a private IP address. It's only capable of having a private IP address inside of your VPC. So what that does mean then is that you will need something like a NAT gateway as well if you want to route to the internet. Now, this is where you want to be careful. This also means that if you put your V2N in, or you connect your Lambda function into a public subnet, then it will not be able to route to the NAT gateway because the default route will basically be required for that subnet to route to the internet gateway. So let me say this again. Again, things that you put in your public subnets can only route out to the public internet if they have public IP addresses. V2N cannot have public IP addresses. And so you must put or connect your Lambda functions to private subnets that if you need to get to the internet, have a way to route out via a NAT gateway. And so you see kind of the flow that's shown here at the bottom line here. Lambda through a V2N, through a NAT gateway, through an IGW to the internet. Have to remember that flow in order for things to work. This is probably one of the biggest areas that I see people get tripped up when they first try to configure things. They say, oh, my Lambda function has to talk to private resources and the public internet. I'll connect them to my public subnets, but then they struggle to figure out why then that doesn't work. Again, here's the reason. You need that V2N to have a default route through a NAT gateway or similar type of proxy in order for that to work. Okay. V2Ns use the security group configured for your function to allow it to access resources in your VPC. So any of the resources that you grant access to, whether you do it by IP or IP range or other security groups, effectively the Lambda function will have access to. So you do want to be careful about if you are reusing security group subnet pairings for the configuration. Yes, that simplifies things and that you'll have fewer IP addresses consumed, but any of those Lambda functions then could hypothetically connect to the resources that are available from that security group. Inside of your VPC, the route table and network ACLs for the configured subnets will apply the same. So if you put your V2N into a certain private subnet, and then you have a network ACL that denies outbound HTTP traffic to other parts of your VPC, that is going to make Lambda not be able to talk to those resources. So again, the normal networking security rules apply to the VTN's interface the same as any other resource that will live inside of it. Also important to note that the V2N does not change how Lambda is invoked. Lambda is still only invoked via its public API today. The V2N is, again, essentially a NAT device. It allows more or less a one-way outbound communication and then a stateful reply based back on that. So from inside of your VPC, you can't ping a Lambda function, you can't tunnel or connect to it directly. That's not something that's possible, and V2N doesn't change that. Okay, so we've covered a whole bunch of stuff so far here. We've covered what VPC is, all the different VPC components that are there that are kind of core and important. We talked a bit here about Lambda networking, the default model where you are not attached to a VPC, and then what happens when you are attached to a VPC. Let's get to some of those kind of more sophisticated, more complicated aspects about this, if you're still with me here today. So let's talk about some best practices and gotchas with Lambda networking, again, in regards to VPC. And I've tried to kind of boil this down to what I felt were the biggest issues, talked to a number of other people. They kind of agreed this was a good list to start with. This represents most of the things that you're going to run into. There are some edge cases and things that you might have, but again, this list represents the big ones. So let's go through them. So the first is, do you need a VPC with your Lambda? Do you need to connect your Lambda to a VPC? I came up with this really basic flow chart that, again, I find works for about 80 to 90% of cases. The first one is, do you need to access resources in a VPC? Do you need to access RDS? Do you need to access EFS? Do you need to access other EC2 services or servers that you're running in EC2? Do you need to access, other databases that might be running inside of a VPC? If the answer is yes, then configure your Lambda function to attach to a VPC. No. If the answer is no, then the next question is, do you need any sort of strict controls around exfiltration or egress traffic? Again, if you're in a regulated industry, this might be a yes for you. However, if you're not and you are comfortable with your developers' practices around writing code, securing code, the dependencies that you use, then your answer might be no. And then lastly, it comes down to, do you need to connect to private resources in any other networks? Do you need to talk to an on-premises data center? Do you need to talk to a colo? Do you need to talk to another cloud environment? Again, if the answer is yes, configure for a VPC. If not, then don't configure for a VPC. If you're only talking to services like DynamoDB and S3 and SQS or SNS or step functions or EventBridge or any of the things that are primarily available just over API, then you may not need a VPC. But again, that's going to depend on your use case and how you're building your application. So real quick, what about CloudWatch? So we mentioned this a little bit before. Again, typically when you are building resources or services inside of AWS, you are utilizing CloudWatch, typically CloudWatch logs, CloudWatch metrics, and the other capabilities. What if you need to get that data out there? So again, by default with Lambda, from inside of any of our runtimes, when you output something, you just generally send a print statement, anything that looks like a console.log statement. We capture that information and put it into CloudWatch logs. By default, that happens from underneath, I like to say, the execution environment. What this means is that it is not impacted by the networking of your function. Whether you are in just default Lambda networking mode or you are attached to a VPC, CloudWatch logs can still be captured. And this actually is by design. It also allows you to be able to debug issues that might be caused by networking at some point. Again, by default, you can just output text. That text will get captured by CloudWatch no matter how you have configured your Lambda networking. But if you want to do custom log messages or custom metrics using the CloudWatch API calls, this is where networking is important to you. And so you will either need internet access out via, like, again, a NAT gateway and an IGW to the public APIs, or you could use a CloudWatch service endpoint, which we'll talk about here in a moment. You also have one other option, which is a really cool capability of CloudWatch, which is called the CloudWatch Embedded Metrics format. And basically, the thing that you need to know about this is that this is a 2-for-1. When you print a message out from your Lambda function, following the JSON standard that we have defined for the embedded metrics format, we actually take that log line and we parse it and we turn it into a CloudWatch metric. So you essentially, with one line inside of your Lambda function, get a 2-for-1 benefit. So this is one way to kind of cheat around the system. You could print these structured JSON logs via, again, a console.log type of message, and it will get captured by CloudWatch and then also turned into a metric. So this is, again, another way for you to be able to get around having to worry about the networking capabilities or configuration of your Lambda function. Again, otherwise, you're going to need to talk to the CloudWatch API, and again, 2 different ways to do that. Typically, I would recommend doing this. It just makes a lot of sense. The embedded log metric format is a pretty cool capability that allows you to use a bunch of advanced capabilities inside of CloudWatch, such as logs insights, which can be really useful for troubleshooting. We've got a couple other talks about observability that you can find in some of the links I'll share here at the end, where you can learn a lot more about this and how it works. But general recommendation, I would encourage you to look into the CloudWatch embedded metrics format. Okay, number 2, this is another really important one. Multi-AZ, or multiple availability zone configuration, is kind of up to you. How is that possible? So from the Lambda service side, we will always be running in multiple availability zones, high available configuration, running at mass scale with a lot of stuff going on. And there's nothing you can do to impact that. But when you connect to a VPC, you're essentially inserting a configuration that could potentially block or impact the value that multiple AZ service capability that Lambda has for you. So let's assume that you had a VPC and you've configured that VPC for multiple availability zones, and you've got subnets across there, but you've only configured your Lambda function for a single AZ. What ends up happening is that the V2N that gets configured only has connectivity in through the subnets you've pointed it at. And if anything happens to that AZ, Lambda is not going to be able to talk to your resources inside of your VPC. If anything happens that impacts connectivity between 2 AZs, Lambda is not going to be able to talk inside of your VPC from one AZ to another. So you want to make sure that you are configuring your Lambda functions to follow the same model as other services insofar as multi-AZ goes. You'll want to make sure that you are pretty much deploying or configuring your function to be able to talk into each of the AZs that you have for, again, fault tolerance, that should say high availability, and happiness, I'll say, at the end of the day. A way to visualize this here, this is maybe looks like a complicated diagram. It's actually really straightforward. We've got 2 availability zones. We've got our VPC that spans both of these availability zones. We then have 2 public subnets, 2 private subnets. And we have our Lambda function configured to talk in through both of these private subnets. We also then have NAT gateways running in both of our public subnets. And so essentially what we have here is the exact kind of redundancy that we would want to be able to sustain any sort of failure of any one of these components. Ideally, with services like Amazon RDS and Elasticache, you're also making use of their multi-AZ capabilities. And again, lots of AWS services have this built in for you. But in the places where you control it, you really want to make sure that you kind of have that N+1 configuration of your resources. Okay, point 3, endpoints for the win. So one really cool capability of VPC that we didn't talk about yet is this concept of endpoints that can exist inside of a VPC. And what these endpoints do is they can represent out to you, or I should say, represent inside of your VPC to you AWS service endpoints. So this uses a technology called AWS Private Link, and Private Link provides a number of capabilities inside of the VPC. But with this endpoint model, what service teams have done is, again, made it possible that you can talk to their services API from inside of your VPC. Today, there's over 90 different services that support this, including services such as SQS and SNS, CloudWatch, Secrets Manager, Parameter Store, service APIs for managing EC2, a ton of different options, Kinesis, DynamoDB, a number of things that you can talk to without having to go out to the public internet. Not today available for Lambda, as we've discussed, but as we've seen the popularity of this, many services have gone on to support it. So assume this is something that we know about and that we're very much thinking about. By default, these private link endpoints are highly available, they're fault tolerant. It's basically a completely managed virtual device, much like the IGW kind of is. It's not something you have to think about. Now you do configure it inside of your VPC, so it does consume an elastic network interface. So that is something you want to think about. And then there are two types of these. One is the interface model, and then one is the gateway model. Now the interface model is, again, providing you an interface to AWS service APIs. The gateway model is providing you access to services that you might be talking to, like S3 or DynamoDB, where you aren't looking to necessarily just configure the service, you're looking to query data from the service. And those are the two gateway endpoint types today. So again, this is a great way to avoid having to go out via an IGW. It has slightly different costs associated with it. Should be less costs, I should say, than going out through a NAT gateway. And again, it prevents you from having to worry about your resources going out to the public internet. Now, it is going to require that you have DNS configured inside of your VPC. It is going to require that you end up configuring security groups and network ACLS the right way. But this could be a great way actually to simplify your networking, to not have to have traffic go out over a NAT gateway or the public internet. And so this is a great way to solve a number of problems all at once. Okay, right sizing your VPC. So we talked a little bit earlier before about this concept of CIDR ranges, of these IP ranges and how that impacts the number of IP addresses that you have for your VPC to consume. And unfortunately, once you do this, there are a number of things that you have to decide, or that you end up kind of becoming, I don't want to say locked into, but that can have a lasting impact on the decisions of how you build your architecture. So if you make your VPCs too small, this could end up restricting future growth. However, on the other side of this is if you make them too large, it could make them harder later on to carve down into reasonable sizes. That said, if you're starting from scratch and you don't need to connect to any other networks, go large. Typically, this means that you are not dealing with, again, a legacy network infrastructure or an infrastructure that lives in some sort of other cloud. And so by going large, you will give yourself the most space to later on carve down and collapse out of that VPC. If you are attaching to an existing network footprint, you are connecting somehow to another, again, cloud or data center or something like that, then you might be in a different space. And again, I'm going to go ahead and presume that you've got a good amount of experience in thinking about network address spaces and how to carve them out. Would still encourage you to, again, think a little bit more about doing this on the larger side. Now, why is this important? So anytime that you launch a resource that is directly in or attached to a VPC, it's going to consume one or more IP addresses. And as it consumes them, it reduces the amount available to other things. So we've talked here about how a V2N would consume it, how a private link endpoint might consume it, how a NAT gateway might consume it, how other services might consume it. And so what you could sometimes run into due to just the way that networks grow, especially if you're using services that support any sort of auto scaling, is that you will have these IP addresses be consumed to the point where you may not have any more left, at which point you start seeing failure. And so this is where you want to be really careful about how you size these networks, how you think about the way that they are built, and really watching out for that potential of, oh wow, I've put too many things inside of this subnet or group of subnets, and now I've got a problem. Okay, next thing we'll talk about here is multi-account strategies. This is something, again, that I find impacts people before they start thinking about it, which is, again, part of the problem. With AWS, we've got a number of different ways that you can do multi-account strategies. The one that I'd recommend is by using AWS Organization. So this is a service that is built to help you manage and create sub-accounts. What we often then see is that sub-accounts are issued to individual teams, other business units, or lines of business that might exist. You might have multiples within certain product groups, and then they themselves might then create separate VPCs. And so you could end up with, very commonly in some of our largest customers, are quite honestly tens or hundreds of VPCs. Now, when it comes to managing them, when it comes to thinking about how to connect to them, how to provide any sort of common services across them, this is where things can become quite complicated. And again, this is a really big topic that we would never be able to give enough justice to here today, but I just wanted to make sure that you were aware that this is something that you want to think about. A couple of basic bits of advice here. If you think that you are going to have much fewer VPCs that are shared or used more widely, think about carving out larger, what are called Class A networks. If you think you will have potentially many VPCs that are either at the business line or at a team level, then maybe you would want to use a Class B network. And then if you think you're going to follow this model where you have lots of teams with lots of small applications and lots of VPCs that are single use case, well, this is where things get a little complicated for you. And so minor joking here, but again, my advice would be to use smaller Class B subnets then. This doesn't apply to everyone. These are pretty broad rules here. I would encourage you that if you are going into a new design of an account structure or a VPC structure, to engage with your AWS account team, to engage with a solutions architect or a technical account manager or professional services or an AWS partner, and get them to help you figure out what is the right model for you. Okay, cross-account access. This is another one that sometimes trips people up. We're going to talk about both cross-account access and then cross-network access. Essentially two different concepts here that sometimes people conflate. So Lambda can be invoked what's considered cross-account. You can give another account access to trigger Lambda functions. That can happen via another service or directly to the Lambda API. And there's lots of good, valid reasons for doing this. Shared services. Typically, I see this used in infrastructure tooling, where you have a Lambda function central account that other accounts are going to want to invoke. My advice is actually to expose the event source to that function versus exposing just the function. And the reason for doing that is that a lot of the event sources that invoke Lambda have controls that can be placed upon them. For example, Amazon API Gateway has things like usage tiers and throttling that you can do. With Kinesis, you have the ability to do things like scale the number of shards. With SQS and SNS, there's a number of controls around filters or FIFO queues or things like that. So there's a lot of different ways that you can handle that. And again, this is just a built-in model, something that Lambda supported for a very long time. But what if your Lambda functions, so not the accounts, but the Lambda function needs to access resources in other accounts or other VPCs themselves? So from a VPC model, one option that you do have is with peering VPCs together. So VPCs can be peered directly to each other in both the same account or a different account, as well as inside of a region or across region or inter-region, as we call it. There's kind of two different ways you can do that. One is with a peering connection, the other is with something called the transit hub. And again, this provides exactly what you would think it does. Private access connectivity between two VPCs, such that the traffic stays always inside of the AWS global network, and that you can use this for connecting between, again, these two networks. Not something everyone needs to do, but again, when it comes to doing this, I find that the peering connection model, super straightforward and easy to do, and typically provides exactly what customers are looking for. You do have to watch out for things like overlapping IP ranges, as well as what's called transitive routing. This is where you want to go from VPC 1 or VPC A to VPC B to VPC C, where B acts as a hub. That is not something that you can do today with peering connections. You can, however, use transit gateways for this. So again, with this, if you've got databases or other API endpoints or other compute resources that live in a different VPC. And again, this could be inside of the same account, in a different account, in the same region, a different region. This is one way that you can enable that to happen. Quick question, or quick clarification on something in this diagram here. So you see that I have put into this other VPC a private API endpoint talking to Lambda. This is a capability of API Gateway. However, with this, the API Gateway is able to talk to Lambda functions that are not attached to a VPC. So again, just because I have my invoke source essentially, as it were, inside of a VPC, it does not mean that I also need my Lambda functions connected to it, because API Gateway is actually going to use the public API endpoint for Lambda to invoke those functions. So again, the network traffic and the invoke path do not necessarily have to be the same thing. Okay. Point 7, using tags for organizing VPC resources. Many services at AWS support tags, including Lambda, including a number of components as you see listed here for VPC. I find it to be one of the things that people don't utilize enough of. I love tagging my resources. I tag them with all sorts of things so I can understand why I've created them, what project or demo they were part of. When I was a customer of AWS, I would try to tag everything with, again, the use case, the environment that it was for. There's a lot of different things you can do with tags, and resources support a lot of tags. So again, with the VPC resources, you can tag almost every single thing that there is. Again, really powerful and useful capability. What can you do with tags? Obviously, easily identify relationships between various entities. You can do things like use AWS config rules to provide an ability for you to remediate issues that might happen with, say, resources that are tagged a certain way but not configured in a way that they're supposed to be. You can do grouping in the billing console and billing reports. You can assign specific IAM permissions to things, such as a developer can create resources in the dev VPC but not the prod VPC and things like that. And so tags can be a really powerful way to do that. And then finally, this is a more recent new capability of Lambda that we announced back in August. And this is the ability for you to use something called condition keys in IAM to be able to control where a Lambda function can or cannot be configured for a VPC. So you could state that a Lambda function can only be configured to your private subnets with a specific security group, or that it can only be configured for a VPC or not to be attached to a VPC. So newer capability, something that a lot of our customers were looking for, and I think this will be beneficial to quite a number of you. Awesome. So again, we went kind of quickly here through 8 key points, things to think about. Again, do you actually need to connect your VPC or your Lambda to a VPC, I should say, making sure that you're taking care of multi-AZ, trying to use endpoints where you can because they're so beneficial, right-sizing your VPC, multi-account and cross-account strategies and access, tags, and then again, being able to use these new condition keys for restricting VPC access. Okay, so we're kind of brought back here again to the question that we asked at the beginning of this tech talk here today. Which one is better? Again, is it this completely serverless infrastructure diagram where we don't have any traditional compute resources, again, or is it this semi-serverless one? Again, the answer is really whatever it is that you need to do that solves your business need. Hopefully you've gotten to now understand a little bit more about VPC, virtual private cloud, and how Lambda and it work together. And based on that, now you've got a little bit better of an idea to understand how you can enable those more traditional use cases, maybe that you've been holding back on, or maybe you have a serverless app and you're trying to figure out how you can use some of these other technologies, but weren't sure how VPC works with it. Again, try to follow the best practices and gotchas that we have here. Again, use a VPC if you need it, but if you don't, then don't. And then lastly, we really just kind of scratched the surface on VPC. Really complex kind of product suite, if you will. It's not even just a single product. It has a lot of capabilities. So definitely go and check out those docs links that I tossed in there and those QR codes. And again, this deck will be made available as will this recording, so you can come back to refer to this in the future. Other places you can go. So you can go to AWS to Amazon.com/serverless. This is our kind of serverless landing page off of the main AWS site. There's a lot of content linked off of here, a lot of stuff to our product docs and product pages that you can find, as well as partners and other resources. And then more recently, we just, my team launched something called serverlessland.com. This is where we are rolling up all of our blog posts, all of our videos, including videos like this one, where you can go and learn about a ton of topics. We've got workshops, we've got various videos that are chained together into what we're calling learning pods, events that you can join us for. So tech talks like this, virtual meetups, a lot more planned on this. This is kind of currently a beta that we've launched, but please do check it out and let us know if you have any feedback. So I think we've got a little bit of time here for questions. I want to thank the team who's been answering the questions for you here in the Q&A box. We hope to see you here again in another tech talk soon. Again, my name is Chris Munns. You can find me at munns@amazon.com or at Chris Munns on Twitter. Always happy to try and address the questions that you have. And then with that, we'll try to stick around here for just a little bit to answer a couple more questions. Again, want to thank you for joining us here today, and we look forward to seeing you at another Serverless Tech Talk soon. Thanks.